Hey guys, today there's a Div 2, and we did pretty well, getting 33rd so far. That's a bit of a step down from winning a round, but you know, what can you do? And actually, part of the reason for this is because, this was during school, sort of, but I was let out early for my first class, so I was able to blitz through the first few problems. And then after that, I had a test in my other class after that, so basically after I solved E, I just had to stop and then just not think about this at all and worry about the test. So it means I couldn't really have any time to think about F, which is sort of unfortunate, but not much you can do. So yeah, we'll get A to E, hopefully, see how things work. There's a chance I might fail system tests also because my E is very close to the memory limit, and I will show you why later. But who knows? Would have been nice to have 1024 megabytes to work with. And in fact, I got MLE on pretest 1 before, so that was fun. And then barely optimized it. But yeah, I'm here to do solutions, so let's do those. I didn't really think about F that much, so I don't know how to do it. So I'll just leave that be. For the rest of them, we should be good. Okay. On problem A, you have to have so you have an array of you have an array. So like for example, 4, 4, and 4. And what you want to do is in one move, you can decrease an element by 1 and increase the next element by 1. You can't do this to the last one. But yeah, so in one move, you can basically move one element from the current position to the next position. That's the way they frame it. What you want to do is you want to do this in a way that makes the array strictly increasing. So I want this to be strictly I want this element to be strictly less than this one, and I want this element to be strictly less than this one. So you want to determine if it's possible to do this or not. So first of all, how we do this in this one. So say we move this over. So we have 3, 5, and 4. Now this is less than this, but this is not less than this, so we have to do more. And so you now move this over, then we get 3, 4, and 5, so it works. Ta-da. Okay. That's one case. How do we figure it out generally? Well, let's say we didn't want to make it increasing. Let's say we just wanted to make it sorted. Then what's a possible really simple strategy we can do? Well, we can just move everything to the end. And that way, we'd have an array of all zeros, and then one final element that's greater than 0. Now, this would be sorted, because everything in the beginning is 0, and then this is greater than or equal to 0. So it would work. The problem is that this doesn't work because we have to make it strictly increasing. But what does it mean to be strictly increasing? Like, say we did want to adopt the strategy of moving everything to the end. Then what are our constraints on our elements? So if we're going to move everything to the end, we have to leave some stuff in the other elements. Like say we have 4 positions. And we're going to move everything to the end. But we do have to leave some stuff in these positions to be able to make it strictly increasing. How much do we have to leave in here? Well, this can be anything. So why don't we just move everything over from this to the end? Or this to a future position to make it possible. So this has to be at least 0, meaning that it can be anything we want. But this one has to be greater than the previous one. So if we're making this one 0, then this one has to be 0 plus 1 because it has to be strictly greater. So this has to be at least 1. Following this pattern, this has to be at least 2, and this one has to be at least 3. And then we can move everything to the end and be happy. So if we zero index the array, then in the final array, this value has to have at least this value each value has to have at least its index. So how do we verify this? Well, let's sweep through the array. And basically we're just going to keep track of the current sum we have. So say whatever this element is. Say we have like 1, 3, 0, 7 or something, right? So we want to make this 0. So we can see how much we need to make this 0. Well, it turns out we need 0. So this 1, we can assume we're going to move it later. So we sort of have like a free 1 element that we can do whatever we want with later on. So it's just sort of like we mash this 1 into our like future pile, and we're going to use it later. Then we look at 3. So this 3 we can also use in any of this suffix, in any element that's before or in any element that's after at this position. So we can sort of say now we have 4 free elements we can use, 1 plus 3, and we have to satisfy this suffix. So what we can do is we can use one of these 4s to make this greater than or equal to 1. So now we decrease 1 from this 4, and then we move on. So we get 0 here, so we still have 3, and we use 2 of these 3s to make this equal to 2. And we move on, we get 8 here, and this works. So if this ever fails, say this element was 1 instead, then we would have 1 here, 2 here, but then we move 1 down, so we get 1. And then we get 1 here, and we don't have enough to make it 2. So that's when it's impossible. Whenever we don't have enough in this process to make the element like this. So that's the basic idea. We just need to make sure every element can be at least its index. And so the way to do that is I used the prefix sum, and instead of directly moving the elements, I just checked if in every prefix, like for example in this, we have at least 0 plus 1 plus 2 is equal to 3 in the sum of elements. And if that's true for all indices, then we're good, and if not, then it's impossible. Because again, the array has to be strictly increasing, and this is the best way we can do it. And we can move every other element to the end. So that was sort of a messy A problem. You may hear that I was not the biggest fan of this contest, because the problems were mostly, I don't know, not new, but I suppose div 2s don't really have to be like that, so I'm just being picky. But I think these problems, some of them are unnecessarily annoying. And I don't know what C2 was. I don't know why they had that. Or at the very least, C1 should have been worth more points, but I'll get into that later. So in this problem, I don't know why it's a div 2b either. I mean, look at this solves. This is too hard. The solution for this is not an idea that comes up commonly. So basically, you have a bunch of points on a plane. Let's figure out an example. A good example like that one. Yeah, sure. So you have a bunch of points on a plane. Let's do this, and then that, and that, and that, and that, and that, and that. So you have a bunch of points on a plane. I'll use their color schemes. So cyan for the actual points. For example, here, 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 and here. And you want to pick some green point. And what you're going to do is you want this green point to be as close to the other points as possible. And the definition of closeness is, or rather like the distance from one point to another is the sum of their x differences and y differences. So normally the distance would be the direct distance, the straight line distance, which is, say this is, say you have to move by x here and move by y here. So you have to move dx to the left and then dy down. Then the traditional distance is like Pythagorean theorem or distance formula or whatever, just square root of dx squared plus dy squared. But we're not doing that. Instead, it's just the sum of the x distances and the y distances. So in this case, it would be dx plus dy. Another way of thinking about it is if we have 2 points x1, y1, and x2, y2, then the sum is the sum of the absolute differences between the two respective coordinates. So what we want to do is we want to pick a green point to minimize this, to minimize the sum of this over all points. So like the sum of distances from this green point to every other point. Okay, now the first thing to notice is that we're taking, so let's write out this equation formally. We're taking the sum of a lot of things. So let the green point be at xp, yp, and everything else be at, like, the cyan points just be like xi, yi for each I. Now we're taking the sum, like the sum of distances is going to be the sum from I equals 1 to n. I'm not going to write these bounds anymore. Of the cost, xp minus xi plus yp yi. Now the idea is that x and y are sort of independent of each other. And the reason is because we're choosing x and choosing y independently to maximize the sum of these quantities. To illustrate this further, let me separate this out. So this becomes the sum of I equals 1, the sum from I equals 1 to n, that's implicit now, of xp minus xi plus the sum for the y's. All right? Now this only depends on the choice of x, and this only depends on the choice of y. So really we're minimizing these two sums completely independently of each other. So we want to choose an x that's optimal, and we want to choose a y that's optimal. And in fact, we want the number of, the problem asks for the number of possible green points we can have. So we want the number of x's that are optimal, and the number of y's that are optimal. So how do we figure that out? Well, once we have both of these answers, we can just multiply them. We have a certain number of x's we can use, for example 3. We have a certain number of y's you can use, for example 2. And all of these combinations of x and y will minimize the respective sums, so they'll minimize the total sum. So really, we just, like, for each x, we can pick any y, so we have 3 times 2 ways to do it. Or rather, if we have cx and cy, then the answer would be cx times cy. So now we have to solve this 1D problem. And I'm not really sure what the point of 1,000 was. I don't know how this would be easier if it's 1,000, but I don't know. I don't know what the point of the constraints was. I mean, it would have been nice if they'd made the constraints themselves 1,000, and that way you could at least get away with trying all points. But I don't know. So so minimizing this sum, picking this point, is a common idea. And the basic idea is, say we sort the x's. Then the optimal xp has to be a median. Now, because this is a div 2b, I don't want to make this take that long. But here's the basic idea. Say we have 3 points. Then I claim the only optimal point is this median. Actually, say we have 5 points. And here's why. Wait, this is totally screwing up my color scheme. So the original points are the cyan points. Because again, we're only considering x, so we can assume these points are on a number line. So let's imagine sliding this green point across. So we have this initial cost. It's like c, right? And so when we move this over, what happens? So we get farther away from this point. We get farther away from any point to the left of the point we just moved to by this distance d. So our cost increases by d because we move farther away from one point. But at the same time, we get closer to every other point also by d. And specifically, we're d closer to this and this and this. Because whatever these distances used to be, now we just cut off, now we just cut off this part because we're closer. So this is c plus d minus 3d is equal to c minus 2d. And because d is positive, that's always better. So we move again. Actually, no, this should be 4d because we also get closer to this one. So, yeah, 4d. Right, and every time we move a distance c, even if this isn't exactly d, even if it's like d over 2 or something, we still get closer to every other point. Sorry, this would be c minus, this would be 3d, yeah. So when we move over here again, say this distance is e or something, right? So now we move e closer to these 3 points, and we move e farther away from these 2. So it's C minus 3D minus E. And then now when we continue and we move past the median, we move farther away from these 3 points. And we move closer to only 2 points. Meaning that now we increase our cost because now we're moving farther away from more points than we're moving towards. So C minus 3D minus E plus F. And then if we move some G amount here, it's going to be the same increase. Or it's going to increase by 3 times G. So this is optimal. The argument is the same for the even. The point is, when you're not at the median, when you move closer to the median, you move closer to more points than you move farther from. So, and when you move past the median, you move farther away from more points than you get closer to. So you can do this argument out, and basically, it's always going to be optimized at the median. Now, the interesting part is, say we have even points. By this same argument, if we move any point between the medians, say this is some distance d, we're going to move farther away from these 3 points. But we're also going to get closer to these 3 points. So it's going to be the same cost. So these 2 medians are optimal. And also any point in between these 2 medians are also optimal. So for odd, the only point that's valid is the direct median. And for even, it's any point in between the 2 medians, the 2 middle values. Again, this only works if xi is sorted. So really that's it. If n is odd, then we choose the middle value of the x, and actually there's only one possibility if n is odd, and if n is even, then we find the 2 medians by sorting, and then we print the difference between them plus 1. Like say this is 3, this is 5, then any point between 3 to 5 works. So that's 5 minus 3 plus 1 is equal to 3. Plus 1 because we have to make it inclusive. You can play around with the bounds a bit and show that this is what you want. So that's how you get the number of x. The number of y is the exact same. So that's it. So in code, yeah, basically if n is odd, no matter what, there's one possibility. Otherwise, then it's the difference between the 2 medians multiplied by each other. Again, I don't see what the point of this was. It uses like, it's either well known or you'll almost never figure it out, or it's like really hard to figure out. So I don't know. You guys can also feel free to complain or praise the problems however you want. But I'm going to voice my opinion. What did they change? Okay. Anyway, this is C now. So I forgot to write the letter, but whatever. So I'm going to tackle both C1 and C2 at the same time. Sort of similar to each other. And I mean, this one was like, C1 is cool, C2 is like just Y. But I don't know. It's a bit interesting. But unfortunately, it happens to be a very common idea in interactive problems. So let's take some array 5, 1, 4, 2, 3. You have a permutation, meaning all values are different. Or yeah, it doesn't. You can assume it's a permutation. The values can be larger, but the point is they're all distinct. No 2 values are equal. So then what you can do is you have a permutation, but you don't know it. All you know is n, the length of the permutation. In one query, you can ask for some sub-segment. I can't speak. And what it's going to do is it's going to give you the position of the second largest element. So this is the largest, this is the second largest, this is the third largest, this is the fourth. So it'll give you this position, which is position 2, is your indexed. You can also use 1 indexing. It doesn't matter. It's going to give you the position of the second largest element. So for C1, you have 40 queries, and for C2, you have 20 queries. And you want to figure out the maximum element, not the second maximum, the maximum. So like, what? Right? What can we do with this? There are a lot of different possible solution ideas that could tangibly work. But what we want to do is rule out some of them, right? So we can't query a single element. We have to query at least one, because otherwise there is no second maximum. So we have to make sure that, like, how can we possibly figure out the answer? If we query any subsegment, we're going to get the second maximum. So maybe there's a solution where we exclude every single index except for the actual maximum, but that's messy. It's not that great. I don't know if there's a possibility there, but I'm not sure. But if we assume that's not possible, because it very well may not be, like how would you narrow down the range? I'm not sure how you would do that, because you only get the position of the second maximum. So we can fairly assume we're not going to actually find out the position from a query. Like we're never gonna ask a query, and the answer is going to be the answer for that query is going to become our answer. But say we do know the second maximum. So the fact that we have 40 queries should be a bit inspiring, because n is 10 to the 5th. And a certain property of log base 2 of 10 to the 5th is that it's about 17, right? Yeah, so it's about 17, meaning that if we were to do some log of n solution, it would take 17 queries. So now we get the basic thought process. It's interactive, so it's probably binary search, and that turns out to be correct. And here's how this works. Let's query the second maximum. So now we know the position of the second maximum. So now we query the second maximum of the whole array, right? So because all elements are distinct, like when is this going to be the second maximum? It's going to be the second maximum only when the first maximum is also in our range. Because otherwise, if this is not in the range, then this is the largest possible element we could have. Meaning that there's no possible way this can be the second maximum if this is not in the range. Because, I mean, it's the second largest. If the largest isn't involved, then it's the largest. So, given that we know where the second maximum is, now we know some criterion for determining whether the maximum is in a range or not. And in fact, there's a certain contiguous segment of ranges where the maximum will be in the range, so it'll be true, and then everywhere else outside that segment, pick a better color, red, I guess. Everywhere else outside, no wait, this makes no sense. There's a certain contiguous segment of ranges. So for example, everything past this point and including it will have the maximum, and everything before this point will not have the maximum. So this would be true, this would be false, and these are the conditions for binary search. That there's some range where negative infinity to x is true, and then like x plus 1 or something to positive infinity is false. So we can binary search on x. We can binary search on the point where it stops being false. We can binary search on this point, and that'll give us this index. And the way to do that is to simply ask a range. If this is the second maximum, then this maximum is in the range, otherwise it's not. And that's it. So for C1, that just gives us 40 queries because we can do a binary search to the left, and then we can also do a binary search to the right. And that gives us 2 log base 2 of n, which is like 34, plus 1 for the initial query, and then that's it. For C2, it's a bit more annoying / involved. And the basic idea is that we're going to do both binary searches at the same time, since we know the element's only on one end. So really, there's no reason we can't do this. That we can ask perhaps there's a better way to do this. I might have actually overcomplicated it a bit. Yeah, there might be an easier way to do this actually. We can say that we're going to take the interval, let this position be p, then we're going to take the interval p minus x and then p plus x. So for example, for x equals 1, that would contain this, this, and this. Then we're going to binary search on the valid x that makes that is true. And then so we just query this interval, and then that way it gets smaller on both sides or larger on both sides at the same time. So whichever side is on, it'll do the binary search in a valid way. That's actually a smooth way to do it. I didn't think of that, but That's kind of cool. Yeah. So we're basically binary searching on the x where this interval p minus x, p plus x contains it. Contains the maximum element. And then that takes 17 queries, plus 1 for the initial one, and then plus an extra query to figure out which side is on. I'll leave that to you. You just like include one endpoint and exclude the other and figure out if it contains it or not. So that takes 19 or 20 queries depending on how you do it. I used exactly 20 because why not? System pre-tests are over. Did anyone solve F? Oh, they did. Okay, nice. I guess that is a thing. Yeah, school is annoying. Okay. I'm assuming F has something to do with like LCAs and I have a general idea. I just don't want to think about it because it's really annoying. Maybe I can go over my brief idea to F and yeah. Actually, no, it's not that interesting. So here's how this works for D. You have an array. Let's take this array. 1, 2, 3, 2, 1. And you have a parameter k. For example, k equals 3. You want to find a subarray with length at least k that has the largest possible median. So same idea of median is b, except better. So with length at least k, we want to find one that has the largest possible median. And the median is the middle element in a sorted array, if that is not well defined. And if we have an array of even length, for example this, then in the sorted array it would be, actually this is not a good example. Say we have the array 1, 2, 3, and 4, then the median is the first one, the smaller one. Is it? Wait. Is it the smaller one or the larger one? Yeah, smaller. Okay, so often when we do problems with medians, or when we're figuring out like the largest answer for some subarray, well, the median has a certain special property. Like, say we want the median to be x. Then if we set, if we like, say like x equals 2, if we set every element less than x to be something like 0, or like negative 1, and then we set every element greater than x to be something like positive 1, then figuring out if some subarray has median at least x is equivalent to asking, does this subarray have positive sum? Because like, consider partitioning the elements that are less than x and greater than or equal to x. If we have all these elements here, say we have 3 elements here and 1 element here, then our sum will be 2, and the positions in the array will be like, so we want the first position in the array that's greater than or equal to x to be like as close to the beginning as possible. Because if so, it means wherever the middle index is, for example, this would be the middle index, it's going to be like, it's going to have a better chance of being greater than or equal to x. So like the number of ones we have is the number of elements greater than or equal to x, and the number of negative ones is the number of elements less than x. And so it's equivalent to asking, does this have positive sum? Because, for example, for the even case, we need this to be greater than this if it's equal. If we have 2 elements that are less than x and 2 elements that are greater, then we have 2 minus 2 equals 0, and then the middle element is going to be the element less than x. It has to be strictly greater for even, and it also has to be for odd. Like, for example, 1, 1, 2, 2, 2. This has 1, or 1, or like 1, 2, 2, 2. This has 2. But it has to be strictly greater than 0. So like, what if we knew what x was? Then we could just say like, we also know the subarray has to be of length at least k. But what if we just said like, let's just find the largest subarray sum of a subarray of size at least k. That we can do in Oven. I'll show you how soon. And then I'll show you how after. And then for this fixed x, we can determine if the answer is at least x or not. Like we can determine we can ask, is the answer at least x, or is the answer less than x? And yeah, so what does that do for us? Well, if the median can be at least x, then it can also be anything less than x, because that's like what at least means. It can be anything up to x, and possibly it could also possibly be something greater than x, but we don't know that yet. We just know that the median can be anything that's like not greater than x. And if the median can't be at least x, then it can't be anything greater than x, because that's what the definition of at least means. So the median has to be less. So the median has to be less than x. This is sort of a weird diagram. But the point that I'm making is that we have the conditions for binary search that we can do. Or it's like sort of the other way. We have some value x, or we have some value y, where every value before y is possible to be a median, and every value after y is not possible. And the reason is simple. Like, when we decrease x, more elements are going to be converted from -1 to 1. Like, say we decrease x from 2 to 1, then both these elements will become 1. So we get a higher chance of getting a subarray with positive sum. And like, if we have x equal to the minimum element, then every element will be 1. So it has to be possible for something. So now, for this binary search, the condition is counting the number of subarrays that are figuring out if we have a subarray of size at least k that has positive sum. And the way to do that is to simply say, so we want to figure out, like, say we do some prefix sums. So we're at position I, and we want to figure out some j that has the sum of at least k. So we're going to have this interval be sum at least k. So let pi be the sum of elements from 0 to I of ai, or like the modified ai, where this is 0 or 1, or -1 or 1. Then we want two things. We want pi minus pj, or pj minus 1. This is every element excluding this, to be greater than 0. And we want I minus j plus 1 to be greater than or equal to k. We want the subarray size to be greater than or equal to k. Yeah, so a separate way of thinking about this is, over all of these, what's the minimum value of this? Or rather, what's the maximum value of -pj plus 1? Because we want this to be as large as possible. If the maximum is greater than 0, then there is a value that's greater than 0. So over all j, let's just maximize the quantity -pj plus 1. And then we can see if pi plus this maximum is greater than 0 for any possible j. So really, we just sort of like we do it like two pointers. We have a current pointer to this, and then we have another pointer to the previous element that's like sort of a distance k apart. And then whenever we get an element that's at least k apart, we can include it in our maximum and then figure out if our value is large enough. So sort of like this. Do binary search, then create the value b, or the modified ai, and then maintain the prefix sums. And then if we're a certain distance from the beginning, then include it in our minimum and then take the best value of this. And then if it's ever positive, then the best value will be positive, so we can increase our potential answer x. Otherwise, we have to decrease it. Yeah. And the way I do prefix sums is I'm also defining it to be like prefix of -1 is equal to 0, because that's like no elements at all. And then I sort of just shift every index by 1. It's just implementation details. You can see my code more if you want. Yeah, okay. U is interesting, but also like not, but also like possibly. Yeah, so how do we do something like this? So basically, the way this problem works is we have a weird graph. Let's say, I'm just going to copy this in actually, because why not? They gave it to us. So we have a weird graph, or even normal graph, a weighted graph. But the way we move through it is weird. We can only move through 2 edges at a time. So for example, we can go through here, but that's pointless. Or we can go through here, we can go through this edge, and then we can also decide to go through this edge. We have to go 2 edges at a time. Yeah. And then the cost for moving through a group of 2 edges, or through a pair of edges. Oh, and also we can obviously only go through edges that we're adjacent to at any point. So the cost of moving through a group of edges is, like say this is C1 and C2. It's the sum of the costs of the individual edges squared, which is like annoying, but that's the idea. Right. So let's figure out how we can sort of make this sort of graph. The point is we want, and at every point we want the shortest path from the original vertex 0 to everything else, or the vertex 1, however you want to think about it. The shortest path from the starting vertex to everywhere else. And if it may not be possible, in that case you would print -1 for that node. So let's consider movement. Basically, we pick some node. We have a starting node. Then we pick some node that we go to. Let's call this the middleman, the middle node. And then we move to another node, going through that middle node and taking the 2 edges. So part of the way we can think about this is relative to the middle node. Let's frame this around 2. We have 3 edges outgoing from it. We have an edge of weight 4 going to node 3. I'm going to use their indexing because why not? We have an edge of weight 3 going to node 1, and to node 4, that's an ugly circle, we have an edge of weight 2. And this isn't connected. So we can move from any neighbor of 2 to any other neighbor for the cost of the sum of their edges squared. So if we draw these edges, if we draw an edge from every neighbor of 2 to every other neighbor of 2 with the cost of their sum of edges squared, that would give us the transition graph. Like this is literally an edge that we can take because this simulates moving these 2 edges. So then using this weird graph, this is something we can run Dijkstra on and just be done. The problem is that one node can have O of n squared neighbors, so that could be a problem. Like we don't want that. But the other important constraint is that the weights are at most 50. And problem setters don't do things for random reasons, if you've ever read Umnick's blog. So why would they make it 50 in a div2e where this is sort of like the constraints are already a pain and they don't give us enough memory and we get really close to memory limit exceeded, and I'm sort of mad about that. But why would they do that? Imagine that we wanted to, we can't directly create these edges, but imagine the cost was normal. Imagine the cost was just like C1 plus C2 or something. then what we can do is, this is sort of a similar thing to converting a min-cut problem on nodes to a min-cut problem on edges. We're going to make this construction. And this is like sort of a well-known common idea if you've ever done flows before. So if you haven't done flows, I'm sorry, this may seem out of nowhere. But if you have, this should be somewhat familiar if you've done min-cut. We're going to split we're going to split node 2 up into like a node that represents going into 2 and a node that represents going out to 2. So here's what we do. We create the node 2 in, and we create the node, I'm not going to have enough space here. And we create the node 2 out, right? Now, we basically do this. Now we have the nodes 4, 3, and 1 on both sides. And this would give us, now we can add these edges in. We can go from 4 to 2 with cost C1. Again, we're working with these modified costs. This is a simplification. It's not going to be that easy. But we can move from 4 into 2 with cost 2. Similarly, we can move from 3 to 2 with cost 4 and from 1 to 2 with cost 3. Right. Now, we can move from 2 into 2 out with cost 0 because this is just going from 2 to 2, right? And then we can move from 2 out to any of these nodes with the same cost that it took to go in, because this is going from 2 to here now. So it's really just like splitting this edge up into its directed versions. Like we have an edge from 4 to 2 of cost 2, and we have an edge from 2 to 4 of cost 2. We're just converting the undirected graph to its directed variant. To its directed equivalent, I should say. And then, so we have the same graph. The problem is, and then this would work, because this is linear in 2's neighbors. This is linear in 2's neighbors. And the number of neighbors in total is O of m. So that's it. This is O of m nodes, O of m edges, or O of 2n nodes, O of m edges. So we're done. Right? Well, no, because we don't have the luxury of this. We have a more complicated cost function. But let's break up. Now we break up C1 plus C2 squared. Let's expand this out. Basic, like high school algebra or whatever. So we have C1 squared plus 2 times C1 C2 plus C2 squared. So this only depends on C1. This only depends on C2. So say we had some way to handle this term. Then all we need to do is make this cost C1 squared, and then this cost C2 squared. So we can make this 4, which is 2 squared. We can make this 4 squared, and we can make this 3 squared. We can do the same thing here. And then that way we would cover these two parts going through an edge. The problem is this part's harder. But it's not that much harder. And again, the reason is we haven't used the fact that the weights are at most 50 yet. But we can do that now, because we only have 50 possibilities for C1, and we only have 50 possibilities for C2. So we want to split these nodes up so that we can figure out what we can do with this. Why don't we just create a new node for each cost? And that way, say we have a node of cost X going to a node of cost Y, representing like this is like at node 2, like a node of cost X and the node of cost Y. Then the total cost C1, C2 would just be X times Y. We know this. This is weird notation. But okay. Imagine again, for simplicity and because I don't want to draw 50 nodes, that the costs are between 1 and 4. So for this graph, what we would do is we would once again, let me figure out a good way to draw this. So we would have 4, 3, and 1. And we would have 4 nodes at each layer. And then we would once again have 4, 3, and 1. So 4, 3, and 1. Now these nodes represent each individual cost of an edge. Because again, we're trying to fix C1 times C2 so that it works. So this is cost 1, 2, 3, and 4. And 1, 2, 3, and 4. Now let's consider going from 3 to 1. So we go from 3 to the node of cost 4 for a cost of 4 squared. Then we go from 4 to the node of cost 3 because we're exiting with cost 3 for a cost of what? 2 times C1 times C2 is 2 times 4 times 3 equals 24. And we go from node 3 to node, we go from cost 3 to node 1, my bad, with cost 3 because the cost from 1 to 2 is 3. So this is 3 squared. So the edge from any cost node, from any virtual cost node to any other virtual cost node is 2 times the product of their costs. So this is 2 times 2 times 3. This is 2 times 1 times 2, etc. So if we add all these edges, and then we add a node from each original node to their cost, and then we add these, and then we can get any path. Any path in the original graph will be represented in this new graph, because we're just breaking up the x squared part into 3 separate components, all of which are accounted for. So this is correct. It's a correct algorithm. The problem is, how long is it going to take? And, well, the other problem is memory. If we have 50 nodes, and then we have 50 nodes, and then we have 50 edges between 50 nodes, this is going to be 50 squared, which is 2,500. And this is per node. So it's n times 2,500. Let's just do a quick ballpark. 2,500 times 100,000 times 4 for the size of an int. That's a billion memory. That's not possible. But also note that some of these nodes are going to go unused. For example, we don't use 2 at all. We don't use 1 at all. There's no node. There's no cost 1 that goes to 2. And similarly, we don't use the cost 5 to 50 at all in either of these. So we don't really need to do this. We don't need to construct this everywhere. We're only interested in the costs we need. So in fact, if we avoid explicitly constructing the new nodes at all, then that gives us O of n nodes in total. Or O of n plus m, I think. Because every edge will only create at most 2 additional nodes, and we start off with O of n nodes, the original ones. So that gives us O of n plus m nodes. How many edges do we have? We still need to construct all the edges for the nodes we do construct. So say we have x. So say adjacent to node 2, we have x distinct costs from 1 to 50. Then we take x memory and x squared edges. So we could still potentially have nx squared, but we don't. And the reason why is, say like we had as many nodes with x possible costs as possible. But to get x costs, we need x original edges in the original graph. Meaning that the number of nodes where this is true for can only be at most m over x. So we have m over x times x squared, which is equal to mx. So that's how much memory we use. We use O of mx memory, or m times 50 in this case memory. The time complexity is, this is the number of edges we have, meaning that we have a log in here because of Dijkstra. So m times 50 times log m times 50. Which is, it's a lot, but we have 4 seconds and, C++. And even though I submitted with the wrong version because I used ints for everything, so it's better to use normal G++, like this, or like the compiler, this still only took 1 second. So, yeah, it has the potential of working. I'm not exactly sure if it will, but we'll see. I guess we can see right now, actually. But yeah, that's the graph we construct. And then we just, the final part is just running Dijkstra on this graph from 1 and then seeing if we can get to every original node or not. And if so, printing their distance. And F, I don't even want to talk about, wait. that's this, right? Okay. And F I don't even want to talk about because I thought about it for like 5 minutes or something, and it wasn't that. Yeah, I didn't really have time. As I said, I was in a test, and then I wanted to start this video afterwards. So, how far did we get? Okay, I guess. How fast is it going? Do we have time to wait for this? 47:57. Did it just pause? Did it just pause system testing right as we got here? Or am I looking at the wrong place? Okay, well, anyway, I don't, yeah. I'll figure out if I failed E. If so, it's mostly just constant optimization, so I don't think it's that big a deal if it is wrong, or if it does get memory limit exceeded. So that's fine. Yeah, that's it. Okay. Hope everything was understandable. I think this problem set was very weird and sort of unbalanced, but I guess take what you can get. Every contest is still a contest. So, yeah. That's all I have. Goodbye.